Anyway, this all came about from a little exploit one of our people found last year in a notable web application. As opposed to yesterday, this topic is on topic for my company's business. It started out with a little bit of text going into an input field on a form. Well, then it was doubled into Unicode. And hacker's dream, page fault reading. You know, when you convert to Unicode, it takes your character, sticks a 0 behind it, your character again, 0 behind it, and things break. In fact, this was plain old Stack Overflow. Anyway, our cast of characters on stage besides me today are just your generic ASCII characters, A to Z, capital and lowercase, a little bit of punctuation and formatting. Why? Because these characters go right through Unicode filters, convert nicely, and they're also transportable over HTTP. Oh, and they make up all literature. In a nutshell, working with Unicode-based overflows, well, first, Chris Anley's paper is just required reading in this topic, and it will really show you how to deal with it. But you end up having to deal with those pesky inserted zeros in some fashion. One of the most useful instructions for dealing with that on the x86 architecture is like the highlighted one there. It has a leading 0 and a trailing 0. So the opcode before and the opcode after don't need those zeros, and you can just use whatever opcodes are useful. The inks are 1 by 8. There's all kinds of wonderful opcodes there. Well, as I was writing my shellcode, I had to try to compact it down to 66 bytes if I wanted to get this really sweet little approach to work. 66 bytes in Unicode is not much. And I kept noticing all these ads, and I wondered if there was a way I could make use of them. I mean, they're free. They just take up space. They pad out the opcodes so they all line up. I can get rid of the stray zeros without crashing. We're not ready for that yet, but with ads, you can just put, what I ended up doing was just adding stuff up. And it's a byte pointer, so it would be adding mod 256, and it's a pointer to just some place in memory. As long as the exploit was working, that was going to be writable memory. So all I did was just add to that destination address and add to it some more and add to it some more. And before I knew it, I had a useful value at that location. Well, I started to write a little shellcode generator. Being a programmer, I wasn't going to download somebody else's. Why do that? You can write your own. Well, I first said, okay, A to Z is valid, so I had a little checkbox for that, and lowercase A to Z and 0 to 9, and well, let's add comma, a period, and space. So I had this nice little selectable range. I was toying with that. It turns out I got stuff that looked like text. I got stuff that looked like base64 encoded data. Well, if I have text, why not go all the way with it? So I did a little number crunching, and I summed up just 4 character sequences from the allowed character set, the A to Z, 0 to 9, and all that. And these were this is the distribution of opcodes that came out of that. At the low side around 0, there's about 5,000 different ways that you can add up 4 characters, mod 256, that comes up to 0. Well, 4 characters. Well, I know a lot of 4-letter words. I wonder which ones add up to 0. That's a pretty good start for shellcode. And over at the peak, around 30,000, let me look that up. Oh, okay, whoops. And our peak is at a convenient instruction for test. Well, that's not that terribly useful, but there's almost 31,000 ways to get to a test instruction. Another right adjacent to that peak is the load string instruction, moderately useful, but there's 31,000 ways in 4 characters, adding them up to get there. Well, could be useful. Then I was toying around with it some more. What if I had to initialize the memory to a specific value first? Well, I noticed that if you did that, it would just, if you used a constant value as an initializer, it would just shift the peak point over. And let me get out. Oops. So this is what you see when you add 32 hex. I just picked a random number. 32 hex is also the ASCII character 2, so that would go through the filters and all that fun stuff. Now we move the minimum points to dB hex, the floating point escape code. Pretty unusable in shellcoding because how much shellcode needs floating point math? Well, and this puts the peak at 6, 7 hex, jump not 0. Pretty useful, so there's lots of ways to get to that opcode just by adding the 4 characters. Well, all right, now we have some ideas on how many different ways we can arrive at specific opcodes. Let's look at some actual shellcode. And here's a graph of Metasploit's bind shell, just the raw bytes for x86 on the Linux platform. I kind of scaled it already. I shouldn't have done that already, but it'll look a little distorted at the moment. But there's not many opcodes in use. Each red line is just an opcode. If it's used more than once, the line just grows taller. If we were to superimpose that first graph, we would get something like this. The peak of the red line is where the most 4-character sequences were. That was, I think, the test instruction. Okay, well, and the other opcodes are just way over there in the minimum area. So there's not a lot of ways to generate those opcodes at the right using this algorithm. But remember, we can shift the point. If we were to just shift it again by adding 32 hex, well, 32 hex, it moves our peak over where we have a bunch of those opcodes that are more represented within the 4-byte string. So there are a fair number of 4-byte sequences that would generate those opcodes when added. So now, if we were to move on to an actual, well, not an actual bit of shellcode, but something representative of some x86 code. If you were to have this assembly sequence, then assemble it, you would get this row of bytes across the bottom in that order. The move instruction starts with B8 hex, and then so on down the row. Oops. All right, so I had to generate those bytes, or bytes like them, for the shellcode I was writing. I wrote a program that would just generate 5 characters. I bumped it up to 5 for this time because of some of those minimums in that graph. I bumped it to 5 characters. Turns out there were a few more ways to get there. In one case, there was just about 4 million different 5-character strings added up to one of these. What I've gone and done is I went and grabbed those files. I picked a few strings out. And I'm going to ask your help in finding possible shellcodes. Okay, across the top we have the opcode byte that we want to get to. Like the first byte for the move instruction was B8. And you have a couple of different interesting strings I found of 5 characters that all add up to B8. Well, anyone take a stab at this? It's kind of like finding the phone number that makes the word. Let's see, if we start with U, comma, H, well, we started a sentence with the word U. That's a pretty good start. There's ahoy, or now ahoy with a space after it. That's pretty good. Or if you want to be funny, you could just rotate the letters and you just anagram them. You'd have Hoya. Any Hoyas out there? Good. All right, so we have a couple of nice ways to generate that first byte. Oh, yeah, there it is right there. Anyway, so now we go to the second opcode, 3D, which was part of the value we were going to load into EAX. Lever, doses. Well, I get things about doses in spam. Anyone seen a pattern here? Come on, just blurt it out. Well, here's what I came up with. Well, it looks like Cialis spam. I probably won't get the Nobel Prize for Literature, but I got some chuckles. Good, thank you. Well, that's just one possibility, but you take, now this is your string buffer in memory now. You have your pointer pointing to it because it was used in a string operation. You just increment across it, you add it to a destination pointer. 5 bytes at a time, you increment the destination, add them up some more, increment your pointer, and then it would decode back into that byte sequence we saw earlier. Well, it was kind of a pain picking the 5-byte strings, and, well, Cialis spam notwithstanding, I wanted to find a better way. So I decided I would start with a classic and see if I could find executable code fragments in a chunk of text. Well, this was the biggest chunk of text I could think of. This was slightly before Stephenson's Baroque cycle came out. It's like this. So this was the biggest piece of text I could find, and I just cracked it open to page 1. I read about 4 paragraphs into it, and this line just screamed out at me. Can a virulent attack be used in a virulent attack? Let's find out. So I wrote a program that would basically just take a block of text, paste it into it, add up, I think this time it was, I think I was still using 5 bytes at this point, so I'd add up 5 bytes, so H plus E plus A, and so on. Store it, jam it, then cast a pointer to it and execute it. Catch all the exceptions, see if registers changed, and maybe it tried to make an invalid jump somewhere into deep memory or just whatever. And if we were to do that with that chunk of text, it ends up looking like this. You add up the first word, the first few characters, you get A6 hex. Compare string, well, if the pointers are valid, it wouldn't throw an exception. An exchange SP, or exchange DX and SP, well, not terribly useful. It would eventually cause your system to crash, so not great for shellcode, but that can be recovered from. A shift, I don't know, but it is executable code just from adding up text grabbed not quite at random out of a book. Well, I was kind of spurred on by this. I mean, the irony was delicious. So I wondered, I just kept looking at text, and I'm wondering how those chimps are doing, if they've hit on anything useful yet. Maybe some source code for an operating system. I don't know what they're working on now, but well, forget it. I went and let's just go to the master now, the Bard of Avon himself. I just grabbed a chunk out of Macbeth. That's why you're all here, right? It's Shakespeare. So let's grab this. When you add them up, you get these values. I mean, they may or may not be opcodes. Let's find out. Well, not yet. They're not. At the first row there, what we have is that original move EAX, call EAX sequence, and then the corresponding Shakespeare text added together. Well, if we were to change capitalization, maybe unspell some things, and we can turn it into malware just by messing up 14 of the 35 characters. It's a pretty decent percentage getting through to convert a chunk of actual text into executable code. And, well, okay, it's still not pretty. All right, I know, still Cialis spam. Well, all right, let's really crank things up. So I cranked it way up to 8 characters. There's 55 billion possibilities there at the peak, whatever that opcode might be. Now, there's 55 billion different 8-character strings. It would take my spell checker quite a long time to deal with it. So I'm opening it up to you guys. So if I can borrow your machinery, just let me kind of plug in here. We'll kind of array them together. No takers? Oh, man, I wanted to find out. And at the minimum side, there's still several hundred million possibilities on the low side. So there's probably some very useful 8-byte fragments that look like text, add up to shellcode. I mean, are we going to ban text? Because now that text can be used as the attack vector, well, if we have to ban text, what's the point of having the internet? Because it was about distributing text and text-based messages and text-based information. I mean, if we have to block text at the gateways, well, let's just shut it all down. Anything, guys? Oh, come on. Oh, yeah. Well, right. What I had run into was a standard Stack Overflow in this one project. It gave me instruction pointer. I wrote this very short, simple shellcode decoding stub. I mean, it was hardly 60 bytes. And it would just go through, it would find the pointer to my buffer. It turns out that was on the stack too, so I just grabbed that pointer, load it into a register, and start decoding. And then the last thing it would do would be jump to that buffer. And because the text portion was so bulky, there's more text than there was garbage characters up at the beginning as the shellcode decoder stub. It would probably get through filters and all that, but it was just a interesting little side effect I'd spotted. I could use text as part of the attack. Anyone else? Oh, yeah. You there? Add, increment pointer. It was a little bit of gibberish, lots of slashes and capital T's, and basically those, well, here, let me back them up. A lot of these, the move instructions, or the add instructions, they were, because of Unicode encoded shellcode, those were just all over the place. And remember, the Unicode conversion adds the zero, so basically it's like 7.6, which is, I believe, lowercase p, 6.8, which is somewhere around m, and just lots of little lowercase, so it was fairly short, and then it was just followed by a bunch of regular text. Just a weird little side effect. All right. Well, last chance. Thank you.